contents jumps high and low of the clock line to indicate when the data line should be sampled or written. This is what one of the data lines looks like by lining the two up and then reading on every rising edge or every falling edge, depending upon which speaker. You can then figure out what the byte is. No, it's not. It's not. The question was, is it Manchester encoded? And no, it's just at the instant of the clock edge, the value of the data line gets latched into flip-flop and held there. So this is so low noise that there's no need for Manchester encoding or other error correction measures. You can tap with syringe if you'd rather not use wires. This is generally helpful if you're just trying to dump an EEPROM. This is a JTAG debugger from Texas Instruments, and the USB device firmware resides in this chip, being executed on this chip. It's rather common that new chips will boot from an external EEPROM chip because the EEPROM silicon is more difficult to make. And when you're also trying to make a radio or a USB device or something that involves complicated analog lines, it's best to keep them separate. Oh. Endoclumata. I like this audience. Having tapped this, there is a great series of tools from Total Phase. This is one of very few proprietary tools that I use. But they make a better product for this than any of the open source stuff thus far. Here you can see the different transactions. MOSI is master out, slave in. You see that data is written here, and then data comes on the other side. These bytes are in pairs because in SPI, a single byte is transferred for every byte that's received. These have to come at the same time, but because that's very rarely useful in a protocol, very often one side of the data will either be ignored or will be irrelevant, or all ones. Having tapped this, you can see delightfully useful things in that quite often the radio implements more than just radio stuff. AES acceleration is one of the best of these. So if you wiretap a, let's say, ChipCon 2420 on an early ZigBee prototype, there are two spots in RAM that actually have the AES keys written to them, and you can just watch the key get written over the line. You can also knock the original host off of the bus and read that RAM out of these chips. So you can say, oh, shucks, I forgot what my AES key is. Could you please remind me? And then you get a copy from which you can decrypt any packet you like. It's also very useful for channel hopping devices because you can tap one device, watch its orders to change channels, and then follow the channel hopping, knowing on which channel to sniff, even though you're not yet aware of exactly what the channel hopping algorithm is. So that's enough an abstract theory. Let's take an actual product apart. This is a turning point clicker. Do we have any university students in the audience? Particularly those in freshman astronomy or chemistry. These devices, for those of you who don't have to suffer such stuff, are used for attendance taking and in-class quizzes and in-class polling. It's also used in some large corporate meetings. The idea is that you press one of the buttons, they're labeled 1, 2, 3, 4, or A, B, C, D, and it will broadcast your serial number, that's these 3 bytes here, followed by the byte of the button being pressed as ASCII. So if you hit the 1 button, it'll do 31 hex, which is ASCII for 1. 2 is 32 hex, all the way to the question mark, which is 3F hex. So you can pop this open just by peeling the keypad off. It's not actually screwed in. You'll find either Philips or Nintendo screws here. You just buy a Nintendo Wii screwdriver and you can pull this right out. Once you're down to the board, you have a radio, which is also a microcontroller. This is an 8051 clone. It's a very early Intel chip that everyone has copied because the patents have expired and that sort of stuff. Down here, you have a SPI ROM. And the SPI ROM is actually used for booting the 8051 chip. Because the 8051 chip includes a radio, it was very difficult for them to also include EEPROM. And therefore, this is necessary to have permanent storage. So there's a little bit of permanent memory that boots from this external memory. There are also these handy debug pins which are accessible from outside of the case. So to dump the firmware, you just have to read up on these chips, discover the protocol of 24C32, and then reading its data sheet, you write a little GoodFet driver for dumping it. The radio itself is an 8051 containing a Nordic RF 2401 radio. The Hope badges use a 24L01. if that's any foreshadowing. They speak at 1 megabit per second, 2.4 to 2.5 gigahertz, 1 megahertz channel spacing, almost exactly the same as the Hope badges, except the Hope badges run at 2 megabits per second. To dump the firmware, all you have to do is run this cable out to the side to one of my handy-dandy GoodFET boards, and if you add USB to your badge, you can run it on that as well. Having dumped it, you send a little command, 03, the low byte of the address, the high byte of the address, and any dummy byte. The chip will reply with 3 bytes of Fs, and then the 4th byte will be the byte at that address. So this is the exact Python code that I wrote to dump the firmware. All it does is send the 4 bytes and read the 4th byte of the reply. These are the opcodes that are used. These are the only commands that the memory chip supports. Having dumped it, this is the firmware. It begins with some length fields out here, and then it has the MAC address in this region, and the 7th byte is actually the default channel on which it broadcasts. Sorry, the 8th byte. The 8051 code begins immediately after that. To dump the firmware, you do goodfet.spy25c dump clicker.hex. This is the exact command that you run today. You copy all of the first few bytes into a binary file. You then load that into IDA-Pro, and you open it at index 0. These are all of the functions properly named. The names themselves can't be recovered from symbol files as they would be within a PC application. So instead, you have to look for port names, which are documented. They're included in the datasheet, and you can very quickly import them into IDA-Pro because there's a maximum of about 100 of them, far fewer of which are actually used. The SPI data exchange function, which is open source, it's part of Nordic RF reference design that was copied by Turning Point in their clicker. This is legitimate copying, by the way. It's like a public domain thing for them to copy. All it does is move the input into the data register. So by searching for this exact line of assembly code, followed by a while loop that waits until the reply comes in, and then something that moves the result into an output variable, you can identify the SPI transaction function. This is what's used to read and write memory. And sure enough, this is the assembly code here. Internally, an SPI port, even though there isn't an external one for talking to the radio, is used to communicate between the microcontroller inside of the chip and the radio inside of the chip. The two are right next to each other but sharing a thin bus. So you can look using these registers and actually identify exactly where the radio code is. These are what the two functions look like. You're either setting the 3rd bit of the radio register or clearing the 1st bit of port 0, and then you're reading and writing your bytes, and then you flip that bit back to end the transaction. This is the function that sets up the radio. If you look deeper in it, you see all of these move instructions followed by local calls. This is how functions are sent. So it's sending 8, 8, 0, 0, 0, bunches of zeros, and then the contents of memory at 1B, 1C, 1D, then these magic constants, then twice the value of 1A that's written incorrectly. You can then look up the format of this configuration string within the data sheet. You can figure out where the width is, where the address is, the address width, the checksumming, the configuration, and the channel number. And you can start running through the code and identifying it because it's just a lot of reads and writes. So this tells us that the channel number, which is the frequency in megahertz above 2.4 gigahertz, is stored at 1A. You've got a MAC address in these bytes. You've got 4 bytes of data being sent, and then 1 byte of checksum. Reading a transaction, you'll soon figure out that these 3 bytes are the destination MAC address, and these 3 are the source MAC address. These are registered names, by the way. This chip has a lot of internal RAM, which is sort of like a register and sort of like RAM. So in any case, each one of these is a unique identifier for a place in memory. It's not a literal constant. But you can search for these things to find the instructions that load them. And this tells us that every single packet is addressed to 12 hex, 34 hex, 56 hex. This number, the channel, and the data rate are all that you need to receive packets. These are packets being sniffed on a Next Hope badge. This final column is the number 5 being pressed. Here you have the serial number. If you do this in a classroom, you can actually get a histogram of quiz answers as they're being placed. And this is the hardware that I used. You can wire up your own badge, run 2 commands, and be sniffing the same traffic. So jumping ahead, I used similar but more powerful oh, yes? So the question is, what happens if the clicker sends 2 answers in rapid-fire succession, such as if one were the legitimate answer and the other were a forgery? There are only 2 ways to do this. You can either accept the first value or the most recent value. If either way, you can sniff the MAC addresses from early in the class period and use it to beat them to the punch. Of course, the software should scream holy murder when it sees this, but it probably won't. Especially as the button might be hit multiple times to cause a legitimate rebroadcast. The radio chain is just copied from a reference design, so I don't really understand any of the analog parts of the radio, except that if you place these components in these places, magic stuff happens. And it runs either the OpenBeacon firmware, which is what all of you with blinking LEDs are running, being tracked and all of the antenna metadata stuff, or it runs the GoodFet firmware, which allows you to sniff it. And this whole thing is built from a GNU toolchain. So GCC was used to build the firmware for all of these badges. They were also programmed by GoodFet. So actually, on the assembly line, every single one of your badges was hooked up to a GoodFet, which flashed its firmware, and also ran a radio test case, which is why only 4 units or so had bad radios. Out of 1,800, it's a decent yield. The GoodFet firmware exposes the radio by USB, so when you want to talk with it, you just write Python code. In the same way that to dump the EEPROM earlier in the lecture, I only had to write a little bit of Python code. Comparing the radio settings, here on the right, you've got OpenBeacon. On the left, you've got the clicker thing. The checksumming is a little bit different, as are the MAC addresses and their lengths, but other than that, they're largely compatible. The Python client is a separate class from most of the other protocols. And it needs a little bit of C code to actually wait for an incoming packet to arrive, but other than that, it's entirely self-contained within Python. There are only 2 functions unique to the radio within the badge sniffing firmware. Within the radio, every single thing is a register. So in order to, say, set the frequency, all I'm doing is taking the value that's given and I'm poking it into memory at the 5th register, or sorry, the 6th register, but 5 hex, within the radio, and then I start asking for packets. The client driver just needs to set up the radio in the right way, and after the radio has been set up, it's the same code to sniff packets. So if you're sniffing OpenBeacon traffic or you're sniffing Turning Point clicker traffic, the vast majority of the code is the same, only the register setup is different. And thus, if you want to add support for something new, such as one of the SparkFun kits that uses this radio, it's just a matter of tweaking a couple of registers. This is the complete function body for dumping firmware and printing it, dumping radio packets and printing them properly and all of that fun stuff. And that's all you need to sniff traffic and clickers and that sort of stuff. You can use similar techniques to hack into other devices, such as toys, the smart grid, sports equipment, medical equipment. This is one of my favorites. Does anyone have one of these? Raise your hands. Neighbor does here. All right. This is the Girltech IM-Me. It is an instant messaging toy for children, manufactured by Mattel under the Girltech brand. I think it had another brand associated with it, which I forgot at the moment. The gist is that you've got a keyboard and an LCD and a 900 megahertz radio. You can then connect to a server, which is running on your home PC by radio, and start instant messaging with your friends without being exposed to internet pedophiles, or more importantly, hogging the home computer. Mattel has an issue with toys, and most toy manufacturers do, which is that there are occasionally extra production runs. You know, the factory will stay open at night, roll up a couple of extra units, which then get sold in the black market, and when Mattel goes to Toys R Us to sell their new IM-Me, Toys R Us says, oh, sorry, we already bought a bunch of them, even if it's their first sale. So as these things roll out of their first factory, they haven't been fully programmed. Instead,